Hello, everyone. Hello, Frank. Hello, my friend. How's it going?
Hello, Denis. How are you?
So far, so good. I'm getting ready for the Christmas and for the winter break. How
Yeah,
about you? Any plans for the upcoming holidays?
yeah, I have some plans. Just let me check if LinkedIn is working. If people are in the chat, they can confirm. But
Yeah, the LinkedIn is up and running, and we have folks watching us right now from LinkedIn. But that's a good that's a good reminder from you. Thanks everyone for joining us today. That's our last episode before the Christmas break. We are not going to disappear. We will take like 2 weeks off, and then in I think that our next episode will be scheduled in mid January, and we will come with some exciting topics for you. But yeah, as Frank said, like let us know that you can hear us, send hi, and get ready with your questions because that's our 15th episode. We started this community open hours. We tried to remember today was the first episode in May or June this year, but nevertheless. And here we are. Thanks everyone who always joins us and watches us online and asks questions. We appreciate that a lot. And thanks to all of you who are watching us on demand later because we know that like not everybody can join this time because some of us start working. For some of the folks, that's early morning. But that's an interesting project. Turns out an interesting project, and we hope that you liked it. So share your feedback with us here and share like your thoughts on what else you might be interested in learning from us next year.
yeah, and not only questions, feedback. Today we have a topic where many people have different thoughts about it, depending on their experience, and then the feedback will be very interesting.
That's a good point because I was checking like if we have any questions from LinkedIn or
Yeah.
any messages. Not yet. Yeah, this topic, the topic for today is collocated and interleaved tables, and that was one of frequent questions that we saw from time to time on our community Slack channel. Yuga by DB, as we know, we do support collocated table collocation, or sort of collocated tables, but our version of collocated tables is different from what other distributed databases implement. And today we wanted just to discuss the concept of just collocated and interleaved tables in the way how they are implemented in other SQL databases. And more importantly, we want to discuss trade-offs because collocated tables is one of those optimizations that you can use to speed up certain requests. But as any optimization, you need to keep in mind a few trade-offs, and we want to discuss those trade-offs with you. And before we start, what else? What else is on your mind, Frank? Anything else before we dive into this topic?
We have some news. We have a new long-term support version.
Okay, all right. YogaByDB 2.20. Do you want me to share the screen, or you want to share the screen? What's the best way for you?
I can share it. Just
Okay.
let me. I realized that I didn't prepare my share screen. It will come in a second.
And
Okay,
while you're
so
sharing,
that's a blog post about the release of 220. So maybe a reminder for the moment. We have the versions number, the the even number are the stable branch, and the odd numbers are the preview branch. So typically production runs on even numbers, and some of those versions are long term. I think I had the definition somewhere. If we search for releases in our documentation, the definition of long term support and short term support, long term means that there are updates for at least 2 years. Because even if we do rolling upgrades, upgrades are always something people have to think about to prepare. So it's easier to patch than upgrade. And then if you don't need all new features, then you can stay on a long-term support and just update it to get the latest fixes, security fixes. But at least you don't have to upgrade too often with the long-term supports.
And this is, by the way, as long as that's the even version, right, 220, it means that we suggest you to take it to production. That's basically also what
Yeah.
the long-term support is an extra thing for you. So before we go into the details, because I checked this blog post really quick, and I personally love a few improvements, but we've got a hello message from our community member Ashwar.
Yeah.
Hello, Ashwar. Thanks for joining. Thanks for being with us. I guess at almost every live stream, it's nice that you keep coming and keep sending your highs and keeps asking you questions. Hope to see you next year as well, and hope to see any questions from you if you find the topic interesting. Okay, so what's in this release? Let's scroll down. We have CDC. We have transactionally consistent change data capture delivered. What is this all about? You know that, folks, those of you who follow Yuga by DB, you know that we have that CDC component that was released, I think this year, if not later, previous year.
Yeah. At least in preview, yeah, I think it was this year, but adding some more and more features. This is driven by the customers using it, so asking for new features or maybe some enhancements. And yeah, CDC basically is what you find in some databases as change data capture or as logical replication. The idea is that everything that is changed, so the DML like insert, update, delete, generate a change record that we can use to apply on another database or stream to Kafka or do some auditing, do whatever we want to do outside of the database. Basically, the DML updates the data in the database, and if we want to stream those events elsewhere, we can use change data capture.
Yeah, this change data capture was but from what I see, because we are about to close this year, and we as the company, as the community, we delivered a lot of improvements and changes to the core database component, like which is the Yuga by DB itself. But there are two other projects that were one of their most successful ones this year. The first one is CDC. And that's exactly what you explained. People use Yuga by DB, and sometimes Yuga by DB is used as a source, sometimes it's used as a sink, and the data needs to be moved back and forth. And this CDC is used widely. We even partnered with Microsoft. Microsoft early this year during the Microsoft Ignite announced their MIDP. It's Microsoft Intelligent Data Platform. That basically allows you to stream data from various sources into their Microsoft Azure Events Hub, and then from Events Hub you can do a lot of analytics, blah blah blah. And we supported that. We became an official partner, and Yuga by DB was featured during the keynote presentation of Satya Nadella. So that's one thing. Also, we use CDC internally. Voyager was the second. Probably the second most successful product of this year. Like it has so huge demand from our users and customers. It's also fully free. It's open source. And Voyager, as far as I remember, the current version of Voyager also uses CDC to stream changes from
Yeah,
between databases. Probably
on
not
other
from.
databases because when you want to migrate a large database, it takes time. So you take the time to take an initial snapshot, but then you want to capture the changes on the source to keep the data live in the target, that is Yuga by DB in this case. For example, to migrate from Oracle, we use Debezium that is doing some kind of change data capture on Oracle. Yeah.
Mm-hmm. As far as I remember, one of the first, like when we released Voyager for the first time, it was using some other extension that was created for Oracle, and But then we decided to replace it because we wanted to support not only the offline migration from Oracle, but also the online migration from Oracle. And that's why the CDC was necessary. So right now, you can do the online migration as well.
I think all databases should support this kind of thing because all environments are heterogeneous, and we have also something. We have customers who move some databases to Yugabyte with the goal maybe to move all their databases to Yugabyte, but you don't do everything at the same time. So there is a point where maybe you will move a few use cases to Yugabyte and stream the changes to the old system. And then slowly the modernization will also be done on the old system. But if you don't want to do a big bang migration, and nobody wants that, probably at some point you may need temporarily, but temporarily for a few months, change data capture to synchronize the different databases or systems.
Exactly. Let's do this. Yeah, enough about the change data capture. What we wanted, we talked a lot, but generally, folks, in this release, it became transactional. Like if you're moving
Yeah.
changes from multi-node Yugabyte DB cluster from multiple tables, all those changes will be transactionally applied to your sync to your
Yeah,
target
because one
database.
big difference with other databases, we are distributed, which means that the stream of changes is not one single monolithic stream. All tablets send their changes, and then the target needs to be able to keep the acid isolation and see the changes transactional, um,
Yeah.
not the half committed thing.
Otherwise you can get some mess, right? Because let's say you're updating a couple of rows, and one row is stored on one node, the second row is stored on another node, and the way you update them, I think it's sometimes the order of the updates makes a lot of sense, especially in transactional database, because you might be debiting and crediting customer accounts, and you want the same change to be transactionally like visible on the target.
Yeah.
All right, so we've got a message from Pete, another frequent visitor of our community episodes and one of our most active Yugabyte DB community members. Hello, Pete, and thanks for joining us today. And thanks for being for starting testing the latest version. Because why I wanted to highlight Pete's comment right now, because Pete, Frank, let's scroll down to some of the improvements that which Pete might be interested in. We have something related to the wait on conflict concurrency control.
Yeah.
And
So there
and
are a few things about caching that improves performance in general, but yeah, a big change is the way we handle transaction conflicts. For example, if you can set the isolation level that detects conflict, and if you run in read committed, um, or other in other isolation level, but especially in read committed, to avoid anomalies, you may want to lock some rows with select for update, for example. And the way we did that before was more an optimistic locking way to do that. For the user, it was the same. The user just waited on the select for updates, but behind it, it was more like a retry logic that detected the conflict and then retry after a few milliseconds and then after a few more seconds. So visible as a wait for the user, but internally it was many retries, which takes more resources than just waiting on the other transactions. So we have implemented wait queues, and that's not an easy thing to do in a distributed database because we want to avoid anything that doesn't scale. So we needed a scalable wait queue where transactions can wait on another. So typically you do a select for update, but there is a concurrent change not yet committed by another transaction. Then you wait on that transaction. You can do nothing until it commits or rollback, and then you can continue when you see if the change was committed or rollback. So basically, this wait on conflict is the mechanism where one session can wait the notification that the other has terminated. So we can expect better performance. For the moment, we even think that it will be better in all cases, even in serializable, because retrying always takes some resource, because you try to do something on the database to write, and then you have to roll back it and then do it again later. So waiting is probably the best idea in many cases.
What I like is that right now you have two options. It doesn't mean that we are
Yep.
going to deprecate the previous approach. You will have two approaches, and both of them are reasonable. It depends on your workload, which means that depending on your workload, pick the mode that works best for you, right? So that you can scale better and so that you have less conflicts.
And
Conflicts.
and that's also where feedback is very interesting for us. Of course, we have customers with support, and then we know exactly what works the best. But one main advantage of being open source is that we have a lot of open source users who will try all combinations. So the combination of wait on conflict or retries, with different isolation level, and the feedback will be interesting for us. If you see that, for example, for the moment, we think that the wait on conflict will be the best in most cases. So if you encounter use cases where the other way is better, then it's also interesting for us to understand why, and to see if we have something to optimize on wait on conflict, or keep the possibility to change because some workloads are better with it.
Okay, so excellent. Thanks for a quick technical deep dive, Frank. While you
And
were
also, just a little thing, when you wait, then you want to know, to have more detail about what you wait on when you troubleshoot performance. And then we have hence the PG lock view from Postgres with more information about what we are waiting for in the distributed Yuga bytes.
Yeah, so those are one of the critical improvements in the core database engine. And as I said briefly, thanks for doing this a spontaneous deep dive into how everything is implemented, Frank. While you were explaining these things, I shared all the links across different channels. Folks are watching us alone, so that's why I was a little bit distracted. But we've got before we go to the next to the main topic of our conversation, collocated interleaved tables, let me briefly answer a question by Eshwar. So the question sounds like this: if you don't mind, can we use LLM, large language models, and generative AI in Yuga by DB? Well, that's a good question, and that's one of the frequent questions we have. Yeah, we can. And right now, I will quickly show you a few resources, and I will share those links afterwards on LinkedIn and YouTube and everywhere, so that you can study and play with this offline, not online, but
And this
offline.
is also something where we would like feedback, because everybody is implementing this in the same or different ways, and the goal is also to see how it is used and what can be improved on it for specific use cases.
So speaking about blog posts, we have a blog post. Generally, what we do, we had an episode about PG Vector during one of our last previous community open hours, where we demonstrated how to build a sample generative AI application using PG Vector. That's the extension of Postgres that allows you to store and process vectors, embeddings that are generated by LLMs. So we will give you a link to that. And also we have some walkthrough articles. We spoke about Azure today. Azure also supports OpenAI. What we announced this week, we started releasing our first tutorials on the technical documentation, and those tutorials will be helping you folks to build applications that need to use Yuga by DB. The first set of tutorials are for Azure. So when you need to use, let's say, Azure OpenAI with Yuga by DB, what can you do? And here is an example of a sample application. and the step-by-step instructions so that you can reproduce it on your end. If you like to watch, I record a lot of the videos, and here is I will give you a link to the playlist about Postgres as a vector database. And the third video in this playlist shows you how to make Postgres more scalable by transitioning your generative AI application from Postgres to Yuga by DB. So just watch this and enjoy. Let me share these links for now. And Frank, if you want to take the air while I'm sharing, please go ahead.
Yeah, I can introduce the next topic then about collocation and
Right.
interleaving, while you are sharing the links about Gen AI. Um, so this is a screenshot from our community Slack, which is public, but I just removed the names. We have many questions that starts like that. Will Yugabyte support interleaved table? This is supported in Spanner, and Spanner is another distributed SQL database, so it makes sense that people ask if we have it in Yugabyte DB. And they say this is supported in Spanner and greatly helps join efficiency. And that's a valid question. And there are also many other databases. Maybe they don't have interleaved table, but they have some other collocation. The idea is that when you join two tables, the first idea is that if you join rows that comes from different nodes, then you will introduce some latency, and then probably it is faster if it is somehow collocated. So collocated in the same node, in the same tablet, in the same shard, in the same place. And those are valid questions, but we also need to think, is it needed? How does it help join efficiency? And then yeah, tons of questions and tons of idea. Is it good to have a feature that helps to collocate?
Because generally speaking, I personally don't have anything against of this feature, but we don't support this feature the way it's supported, let's say, in Google Spanner or where Amazon Aurora Limitless, and there is a reason why we don't support it. We might support it in the future, but right now we don't see demand, and the trade-offs actually, we are not that happy about the trade-offs. So let's discuss it. But anyway, folks, don't get us wrong. We are not diminishing that feature. We just want you to understand the pros and cons of those collocated and interleaved tables, because for every advantage you need to think about a possible disadvantage. Okay, so the article that we created and we discussed it with you 101 before. Let's start with it. I'm sharing my screen again.
And basically, we are not saying that we will not implement it, but we'll not implement it just because Spanner has it. We will implement it if there is a need for that, for which there are no other better solutions.
Exactly. So let's define the collocated tables first, and we will be using visuals. We engineers like to see some diagrams and some pictures. So imagine, let's talk about collocated tables first. Imagine a simple use case. We're working on we have some e-commerce application. It can be some website that sells different goods from different merchants. There is one that is very Etsy. Etsy is one of the most fastest growing websites, online shopping platforms in the United States. Basically, if you can do something with your hands, like toys or tables or anything else, you can sell this on that Etsy website. And imagine that you have customers there, and customers buy stuff from you. So let's say we have this customer table, we have this order table, and here is we are using this coloring scheme. For instance, all the orders that are in blue, they belong to the customer number 1. All the orders that are in red, they belong to the customer number 4. So hope it makes sense. We have this table, we have some tiny data set, and then we are building this e-commerce application. We are expecting to have how many? Millions and millions of active users daily. That's our goal. We are shooting for the stars. And from day one, we decided to start with a distributed database. We are not putting any specific names here. Let's say we picked some distributed transactional database. It has to be transactional. That's one condition, because we are dealing with some real data. We cannot allow inconsistencies. And by default, the database distributed data evenly, meaning that it will try to make sure that every database node keeps around the same number of records, like around the same data set, so that you can evenly utilize your storage and compute resources. Which means that, let's say we have this customer number one, and customer number one is stored on the first node of the cluster, right? What's about the orders of the customer, of the first customer? All right, one of the orders is stored on the same database node, but the second order is stored on the second node. It might happen because what the database does, it just tries to distribute all the data evenly. And in return, you can see that pretty much every node stores comparable data volume. And this is what I think, this is what Yuga by DB, this is what Google Spanner, this is what I know, Cockroach do by default. All those distributed SQL databases. This is how we distribute the data. All right, now collocated tables. Here they are. The purpose of the collocated tables is to store child table records together with the rows of a parent table. So in our case, let's say that we define customer as a parent table. Why? Because every customer has orders. So the orders is a child table. And then you enable this collocation capability. And once you do this, all the orders that belong to a customer are stored together with this customer on the same database node. That's what we see on this picture right now. For instance, we have these orders belonging to the first customer. They're stored on node number one. We have customer number three. All his orders are located on a different node. So this is how the collocation looks in practice, right, Frank? Anything else to add here?
Yeah, that's the way visually we see that join should be faster because you join rows coming from the same node or shard.
Mm-hmm. Mm-hmm. And if you start Googling, if you start reading some resources about these collocation tables, then usually, yeah, you would see that the explanation, justification, why the heck would we need to have these tables for joins? That's exactly what you're telling, my friend. Because right now, let's say that I have some query, some business query. My application needs to say like how much has customer one has already spent with us. It can be some business analytic. Or let's say I'm taking this mobile phone and I go to my orders list. I want to see all the latest orders for the last couple of weeks. And man, and I think, man, like if you live in the United States, at least, usually you do this frequently because you have your partner, and your partner can go and just shop really frequently. You want to see what was where all your money went. You want to see like what exactly was purchased. And if you want to see that stuff, all such a request that joins, let's say, customer table with the order table will be handled by one node, because that node stores all the data needed for this query, for this join. That's the benefit. That's an obvious benefit. Oh, what else? What else? Interleaved tables. Because collocated tables, you spoke about Spanner, right? But Spanner's, when you Google for Spanner, you will find that Spanner talks about interleaved tables. So, Frank, I'll let you explain what an interleaved table is and how is it similar or different from the collocated tables that we have just discussed.
I think it's just a step further, thinking that it's better to have the rows in the same node. Then the idea is that we have them in the same block, because behind the rows are stored in blocks. So you don't even, you have a collocation in the nodes, but you have also, they are close together in the memory. They are close together when you do a disk IO. Maybe you will get the order information with the customer information. We can even think that this can fit in the CPU cache with a few orders for a customer. So the idea is really that you get everything at once when you query for a customer and its orders, then they all come together.
Yeah, it's certainly better from the disk IO perspective, because as I said, the same block, right? You're reading this block, you're reading this how much 32 or 64 kilobytes from disk, and all the data is already in this block. It's also good from the memory standpoint, right? Usually all that you have this customer record, and all the customer orders are stored one by one in the same memory page, which means that like you're reading this memory page from your DRAM, whatever, or it can be even cached in your LLM cache of the CPU. It's fast. Uh, and there,
We can also put it in another way. It's kind of you already pre-joined
yeah,
physically the rows.
and this is actually we discussed this with you. This is so much reminds me of document databases. When I came across this interleaved tables for the first time, I started thinking about MongoDB.
Yeah.
Because even if you take a look at this picture, so here is folks, one important thing. So the interleaved tables, yeah, like think about those interleaved tables as a special class of collocated tables. Similarly, as collocated tables, the interleaved tables first will store your customer and order records together on the same node, but then the child records, like the orders, will be physically stored in the same table structure on disk or in memory. But logically, on the application layer, you will still have separate two tables, like customer and orders. They will be separate. They physically are stored together on the same node. And this is reminds so much, even if you take a look at this picture, it reminds so much of the document databases when, let's say, you have your customer record and all those documents are stored in JSON or like JSONB, whatever, together. So it's very similar.
And the marketing message from those databases were do not do join, do not scale. But actually, I think they did that. The problem was more than performance. The problem is also the consistency of data. It is more difficult to keep data consistent when they're on different nodes. If you process them as one document, so only one read operation or only one write operation, it's easier to get that consistent.
Exactly. So, because in our case, take YugaByteDB or take another distributed transactional database, we don't limit you if you need to update multiple records stored in multiple tables. We let you do this because our database transparently will coordinate this transaction, ensuring atomicity, consistency, and durability. So from the user standpoint, it feels like you are working with a single server database. But Mongo is not a distributed database, which means that when you update this, and it's not even, yeah, and if you take a look at this, they suggest you to store documents because it's easy to update this transactionally from the transactional standpoint. If you start updating the records within a single transaction that are stored across multiple tables, you would need to create a more advanced version of the transactional protocol. And I think that probably right now they already support this. I think that Mongo advanced its transactional capabilities, but one of the first versions of Mongo that I remember, yeah, that atomicity was possible to achieve only on the document level, meaning that if you wanted to update data stored across several documents, several tables, then there were a lot of trade-offs. It might not be consistent at all times.
And
Anyway,
today, even if they have some transaction, some transaction or the multiple documents, the performance is not the same. Yeah.
you know a lot, huh? How do you know that?
Because
Okay.
I like to see the marketing messages from NoSQL vendors and see exactly what is physically behind.
Okay, enough about Mongo NoSQL. It's generally like this interleaved table will remind you folks a lot of the document databases such as MongoDB. To summarize, collocated tables, right? Before we go to the trade-offs, in the collocated tables, you can store records of your child and parent tables together, like here. They will be stored physically on the same database node. We have customers and all the orders of the customers are stored together on the same node. And that's good from, let's say, from the join standpoint, because you join like here and all the data is on this node. There will be less round trips between the database nodes if necessary. Interleaved tables is a special class of collocated tables, all the records of parent and child are stored together, but not just on the nodes, they're stored together physically in the same table structure. And this is what a Google Spanner does. Now, before we go to the trade-offs, let me quickly check the questions. Do we have any questions? Let me pause here. I need to refresh our LinkedIn. All right. No, good. Yeah, good to go. Speaking about trade-offs, the first one is data and load skew. You want to talk about it,
Um,
or you want me to talk about? I can start, and you can give her more.
yeah. Just start and yeah.
Okay, so the data skew. So what's the data skew? The data skew, folks, it's a well-known term, and I think that it's already widely used within our industry. The data skew happens when one of your database nodes starts storing more data than the others. It consumes more storage space than the others. That's the data skew. And sometimes the data skew might lead to the load skew. The load skew happens when one of your nodes processes more requests. How data skew is possible with the collocated tables? Just keep this in mind if you decide to use collocated tables. So even right now, we have this very, very tiny data set. And take a look what happened. The first and the third node, they store approximately the same number of records. Like 2 records, 2 orders here, 2 orders there. What's the problem? But the second node, it stores 5 orders, and 5 is bigger than 4. So like this node stores more orders than the other 2 combined. It's a little bit unrealistic use case, but like when you talk about production data, we might be talking about hundreds of thousands of records differences between the nodes, or even more.
And
And why
here
this
we
is
distribute on the ID of the customer without really knowing how many orders they have.
exactly. So what the database did first, the database took your customers and then distributed those customers evenly. So first customer went to this node, the third customer went to that node, second customer went to the second node. What to do with the fourth customer? All right, the database decided to store this fourth customer on the second node. It might have been stored on the first or the third node, but it ended up here. And then when we were storing the orders, we using the orders table is collocated, meaning that the orders of the second customer and fourth customer are stored together. And that's how you get into this data skew. So already right now, it's I wouldn't call it data skew right now because the difference in the orders number is negligible. But what happens next? Let's say that you're preloading some like a little bit bigger data set, and let's say that turns out that the first customer and third customer are frequent shoppers. They truly love your e-commerce application. They return to your e-commerce application and they buy a lot from you. Like we have a lot of people, those who live in the United States, they will understand me. We have this Amazon, we have this Target, we have this Walmart, and come on, like almost every week you just go online and you just buy something. You buy something from them, which means that you're putting more and more orders. And some of those frequent buyers, they will be generating a lot of the orders. So what we see here right now, the first customer, yeah, he already put 130 orders in the system. Customer number 3, that's the winner. He already put 280 orders. Customer 2 and 4, like actually they are modest buyers. They don't like to spend a lot on our shopping platforms. I don't know why, but generally we've got this data skew. So right now, even if this node stores 2 customers, from the order standpoint, this node consumes much more, which means that also this can lead to the load skew. This node and this node will be processing more workloads. More data needs to be processed if you want to run any requests for the third customer and its orders and for the first customer and its orders. So this is the data skew. So get ready for this. If you're using the collocated tables, that's the first thing that will happen, will definitely happen in production. I saw this in practice when I used to work at previous database company, and we used another database product, and that database product also supported collocated tables. So this is something you have to keep in mind. So get ready.
I've seen some real life use cases because people may think that all in all the number of order on average will be the same. but applications that we run on SQL databases are always complex. And I've seen these cases, for example, for coffee vendor like Nespresso, where they had the same application for the e-commerce, so the customers ordering coffee capsules every month, for example, and in the shops they were just using a special customer ID. That was the shop, and
Hmm.
in that case you have some customers with one order every month, and you have some customers with thousands and thousands of orders a day. And I remember that we have always also seen that for normal customers, because you may think, okay, the application has to manage the shops differently from the customers, but we have seen that also because one of the customer was an hotel, a chain of many hotels, and they ordered the coffee for all the hotels
Ah,
in one
okay.
order. And you can imagine the size of the data that is behind that. So many orders for one special customer, and that's quite difficult to manage from the application, because at first you don't really know, and then you come with this kind of skew where one customer will take all the space in disk, in memory, and in CPU activity on one shard, and you will have a hotspot on it.
Yeah, and then you would end up doing what? You would end up allocating a special database node just for these few big customers, right? And you would have this
Yeah,
maintenance nightmare and migration nightmare. It's, yeah,
because if you decided to interleave, you cannot really split it.
yeah, you cannot. I can, like those of you guys, we will share this. I will share this article in the end. But here is I shared how we at my previous company, because we had this use case, and that was a payment, like it was a payment application. You would need to swipe your credit card and etc. And it also was related to merchants and customers. Uh, you would, for instance, if you want to split this customer, right, you need to split this customer record in two if you want to redistribute the orders, which means that for the customer you can introduce the concept of a bucket. Let's say first bucket and second bucket, and then you add uh, the first customer, the first bucket, then the second bucket for the same first customer, and the third bucket for this customer. And then when you are adding your orders, in the order ID, as part of the primary key of that order, you also need to define the bucket number. And by that, kind of, you have several versions of this customer that belong to different buckets, and those orders will be distributed across those buckets. But that needs to be done on the application layer. So get ready for that.
So in
So
addition to the business logic, you have a lot of code just to handle the physical location of the data. And when we think about SQL databases, the one goal of the relational databases was the opposite, this physical logical independence, where the application doesn't care about where is the data. You can create indexes to do something physically on data, but the application, it's transparent for the application. There you need to handle that in the application.
mhm. Yeah. All right. I think that data skew, we discussed it to death. That's the first trade-off that you would have to collocated tables, and in my practice, everyone would have it sooner or later, unless your application service is used just by a few hundreds of people. Yeah, if you use at least, if you have thousands of active customers, then get ready for this. Another trade-off, the second trade-off, is the best parent for
Yeah, and to
collocation.
introduce it, I can ask you a question, because we have seen that you have pre-joined customers with orders so that the join is faster. But how do you know that we will join customers to orders and not orders to products or to anything? That's also the value of SQL databases. They can handle multiple use cases. This is why the join is done at runtime, because you may have different views on your data. Here,
Hmm.
you have one specialized view that is optimized physically, but then what about the others?
Hmm. Hmm. And let's do this. Let's make this schema looking a little bit more realistic. How about we introduce this sold products table? Because when customer buys something, like we have this order, but usually you don't store the items from the order in the table. You have a dedicated table. And let's say all those sold products as part of the order are stored in this table. You have, let's say, every sold item has ID, it has order ID, it was purchased from, it has product ID, because actually that's you purchased some product like Nespresso capsule, and there are different flavors of that of those Nespresso capsules. And then you decided, all right, like you were building your application and you discovered that, yeah, for some of the queries I need to join customer data with order data and with sold products, because sometimes I want to see, all right, show me the details for my last 3 orders. I'm going, let's say, to Amazon or to Target mobile application. I'm going to my orders and I want to see what exactly I purchased in those orders, right? What were those products that I purchased? And will actually make that join faster, because the data of orders, customers, and sold products is stored together on the same node, and you collocated it this way. But then you'll be testing, then and then the business folks come. Yeah, and this is actually how it was distributed. So those usually you have, if you have, let's say, 130 orders from the data skewed perspective, then you would have much more products that were purchased through these orders, right? So like take a look at this frequent buyer, like customer number 3, who already put 280 orders, and across those 280 orders he purchased more than 1000 items. Like, the data skew problem will be getting a little bit more tricky, but that's enough for it. Then someone from the business team comes and says, hey folks, uh, we need to prioritize another microservice, and that microservice will be for merchants and company logistics and business growth. So with that microservice, we want to track and forecast the demand and availability of various products in our e-commerce application. So by implementing that, the company can boost sales, like every company want to earn more. And also the merchants will be able to proactively restock their products. Excellent, right? That's a good reason. And then you have those 2 other tables. You have a merchant table, the guys who actually sold the products to our customers, sell the products to our customers, and we have the products that are being purchased. And you're thinking, all right, I've already I've collocated orders with the customers. Why don't I collocate products with the merchants? Because sometimes I need to quickly find all those products that are available from a particular merchant, and that will be fast join. But then you have this sold products table, and you're thinking like, okay, how should I collocate this sold product table? Should I collocate the sold product table with the customer, because customer is the one who puts orders in the system, and all those sold products belong to an order, and that would help me to optimize the set of joins and requests for this part of the application, probably for customer facing application? Or should I join this sold product table with the merchants and products? Because generally, yeah, those products that were sold in those orders, they belong to one of the merchant, and that would help me with my like forecasting microservice that would help me to forecast and boost sales. And here is the challenge: you can join child table only with one parent table, and you have to make this choice. So in this way, you can join the sold product table with customers or with merchants, and you have to pick. And that's exactly what the best parent for collocation trade-off means. So sometimes, and you can realize this when you're already in your pre-production phase, so when you're already in production, that, oh, come on, I collocated this table with the customer, but this table is necessary right now for this part. Like, should I decollocate it, or like, what should I do? So
And
that's another trade-off.
and the two use cases are critical, maybe not at the same time. In the life cycle of an order, uh, it can change. I mean, when a customer is taking an order, of course, all the items should be together. But then after a while, it is about sending the order, doing some marketing analysis on it, and then the services, the use cases change.
Mhm.
Basically, by collocating too much, like interleaving, we are going to a hierarchical model from a relational model that has this agility of multiple use cases to a hierarchical model that has a single point of view on the data.
It's like it reminds me of this denormalization approach a little bit. I remember the times when Cassandra was the thing, and in Cassandra you did not have joins, and the approach was similar to what Mongo does. You would store stuff, you would store data from various tables together so that
Yeah.
you can run fast requests. And this way, and then like the guys who worked with Cassandra, they were telling me, yeah, usually in the beginning it's fun. You would be defining your schema based on the queries that are necessary right now. Let's say for your first release, you needed to support this set of queries, and you denormalized your data in Cassandra following their demands for these queries. But then later in production, half a year later, another queries needs to be supported. And come on, what you need to do? You would start introducing other tables that store duplicate copies of the record, and it gets into a nightmare. So
Or
with Scala,
stream the changes to another database that is organized differently, and then handle the synchronization between them, and maybe add an overhead also on it. And
yeah, with collocated tables and interleaved tables, basically you're getting into the same, it's quite comparable territory, because by collocating or interleaving tables, you're fixing them. Making the structure static, meaning then it will be hard to break it. Yes, you will optimize with those collocated tables. We will certainly optimize a subset of your queries, but think about the stuff that your system is going to evolve, hopefully. It's going to change, and the set of queries is going to change. And is this collocation relevant for the future? Sometimes it's impossible to predict. That's why, uh, to stop on this point, let's say that what are the alternatives, Frank? Let's say that we don't want to use collocated tables for any, like, for probably we just right now we're aware of these two trade-offs: data
yeah.
skew, load skew, and the best parent problem. And we decided, all right, okay, so let me trust to the database. The database, like, that's the first picture, right? The database will distribute all the orders, all the data evenly. But how can I optimize my requests, my joins, considering this data
Then
distribution?
if we step back, the first idea was that joins are slow, and then it's better to avoid joins. But then let's just improve the joins, because databases, relational databases, are made to join, and they have a lot of different algorithms, optimization, cache that is optimized to join the tables. So my first idea when I have a question like that, thinking that collocating will be faster, let's just try to improve the joins first. And looking at the time, maybe I will share my screen. I was running during that time. I was loading some data. I have the detail in a blog post. I was loading a data on two tables that I call one and many, because I have a one-to-many relationship, and I can check the size of those tables. In one, I have 500,000 rows. I just loaded that while we were talking, and on many,
Mm-hmm.
I have a bit more rows. I've built that with many rows. So that's 80, sorry, 8 million there.
And
And
while you're loading, we've got a question from Eshwar about the
yeah,
collocated table. So I saw this question, Eshwar. Yes, stay tuned with us. We will answer it in a few minutes.
okay. And then just doing my select that was joining. So the idea was the same idea as the question on Slack. It is joining the two tables, one and many, and with a limit. And that's usually where the problem is. I have a criteria on one table, but a limit at the end after the join. And let's just do the join. So those tables have 100,000 of rows for one and million of rows for the other. And the join to get the top 42 rows there after the join just takes a few milliseconds, because actually we never see in the execution plan we never see 1 million rows. And this is the way where we can optimize something, having an execution plan that doesn't depend on the size on the table. So of course, for that, I created the right indexes. I have an index on scan that reads only 9 rows, those that are in the category I'm looking for, and another one that reads only 5 rows. And why only 9 and 5? Because I don't need to sort them. I'm
It's already
showing
sorted, right?
again.
You don't need to move the data between the nodes. That's right.
Yeah, and the goal was to join and then sort them with order by to take the top 42 ones there. If you join millions of of rows and then have to sort them to get the top n, that
That's
can be
problem.
slow. So you need to create indexes where you don't have an additional sort, and you don't need this additional sort if you have the right indexes that returned the rows sorted. If I look at the index, but I can show that in the blog post. Searching for the create indexes. So I've just created 2 indexes to allow this join to be fast. So I filter on the category, then I need to start this on the category. Then I order on the create date, and then I have it, descending order. And then I have the ID. The ID is used to join. And because I have it there, it will be an index on scan. So those are the best indexes for this kind of query, for this join, especially with a criteria on the category and needing to get them in order. So basically, I'm not saying that we can do any kind of complex query with joins fast, but before thinking about doing a very different physical layout in the database and with impact on the application, before that, be sure that you have the best indexes. And of course, we also optimize something in Yugabyte.
Let's pause it here because folks, it's important what Frank showed you. Indexes still exist in distributed databases, the same indexes that you use in standard database, single server database. They exist in Yugabyte. So run your execution plans, see like the execution plan and optimize it. Sometimes you need to create an index. Sometimes you need to drop an index, right? If the execution plan doesn't work. But what Frank showed you, that's one of the tools. Another one is, let's quickly list a few other items because we've had a few questions. We had a question from Eshwar, from Pete, and then you would close this.
Yeah,
so what else?
We have also a batch nested loop. Here it's not useful because I need only few rows, but we have also a batch nested loop to be sure that if we join thousands of rows, we don't have 1,000 times the latency between the nodes. So we read 1,000 of rows and then we send that to the other node. We push down the join condition to the other node, which means that if you join 2 tables, okay, you will have the latency between the nodes, but you have it only once. So you have 1 millisecond or 10 milliseconds, but once every 1,000 of rows, not once per rows. And this is how it can scale. So we prefer to improve that. And maybe I can add also something. With indexes, we have global indexes. We can distribute the index without any constraints. That's different from the sharded databases, where you can have only local indexes and maybe you have less flexibility on indexes. Here, we can really create the best indexes for the queries.
Exactly. All right. So you showed the indexes, and the covering indexes also is a good technique. You just got the best matched loops. You just got the global indexes. Speaking about actually, just to highlight how it works visually, like the batch nested loops. Let me share my screen right now.
Yeah.
I will get back to this article.
Sorry.
Oops.
Yeah, share it again. Yeah.
So here is, folks. Imagine that we want to join. Want to join the orders for the first customer. So the request comes here, and let's say that I'm storing, let's say 300
orders here for the customer one, 200 here, and 500 here. It's not shown, but generally this node will be joining this data. So the first subset of their orders for customer one will be here. The other orders will be on the other two nodes. And then this database node, if you enable those batch nested loops and if you increase the size of the batch, this first node will send just one request in parallel to the second and to the third node, and those will deliver the remaining data really quickly. That all happens in parallel, and we are talking about just the speed of your network, right, Frank?
Yeah. For the moment, to have this batch nested loop, it's not by default. Let me just share my screen
I
to
show
show.
it, yeah.
For the moment, we have a parameter to set that. The default is 1, so it's not patched, and it will be soon set by default to the maximum, which is 1000. For the moment, either you set it on the session or you set it with an int in the query.
Okay, so you have options. Let's get to the, because we want to be mindful of your time, folks, because Frank and I, we can keep chatting for hours, but we're already beyond the hour, which means that we have to get to our questions. The first one was from Eshmar. Let me find it. So the question was about collocated tables, how it is decided, how do you actually collocate data? Let me show the article one more time. So here is, if I scroll down, I had a schema. You see this customer table, and we decided that this customer table is the parent one. And we have the order table. In the order table, you need to introduce the customer ID, which is usually presents, right? Customer buys orders. And in your schema definition, you will say that the customer ID is the collocation key. And the database will be using the customer ID to decide on the placement of the order, which means that all the orders that have the same customer ID equal to 5, they will be stored together, because this is how the database will take the customer ID, it will calculate the hash code, and based on that hash code, these orders will be mapped to one of the nodes. Hope it makes sense.
And there is also a good remark. How is indexing the primary key here is quite easy because it's collocated on the primary key. But for example, if you want an index on total money, this one will not be collocated.
Mm-hmm.
Because the index, it will be sorted by the amount of money, and then one entry may address multiple orders that may be on different nodes. So that's also a good remark, that this hierarchical point of view with interleaving or collocating, it's collocated on the primary key, and then the secondary index pay the price that it's not collocated.
Mm-hmm. Because if you don't do this collocation, let's say that this orders table is not collocated, then the database will decide on the hash code of the order ID about the distribution. So, and like, even if, let's say, orders have the same customer ID, the database, their IDs will be different and they will be placed everywhere. But once you introduce this collocation, once you say that, all right now I want this customer ID to be that collocation key, and then suddenly all the orders will be stored together because they share the same customer ID. So that's how technically it's usually implemented. But the syntax varies from a database to a database, how it's exactly specified in the create table command. So what's next? The question from Pete. Where is it? It's here. Hierarchical storage interleaved, as it's known, and calculated risk mostly do with access via the top entity, but denormalization is probably a step back. Try not to avoid to store items double unless you create a deliberate index payload for good access. Yeah, I think that was a remark for the part of the conversation when we discussed denormalization as well. Yeah, that's true. Yeah, before we start, let's say denormalizing. I think that's it. What I like about this view is that before you start thinking about denormalization or collocation or interleaving, try to see whether more general purpose solutions are suitable for your use case. And indexing is a more general purpose solution, right? Well, batch nested loops is also general purpose stuff. If nothing works, then start thinking about denormalization and interleaving, whatever.
Yeah, exactly. Because indexes also introduce some redundancy, but it is automatically maintained by the by the database, and it is transparent to the application. When you have to do it yourself, then you have to change the application, you have to maintain it yourself, and yeah, more difficult.
Okay, so any other questions? I'm checking the channel. I guess that I think that we answered. So yeah, hope. Thanks, Pete and Ash for taking part in this conversation today. Unfortunately, you're not joining us live, but thanks for guiding us with your remarks and questions. So, Frank, let's do this before we close the stream. Share your article.
Yes.
Share your article on LinkedIn and also here.
Yeah. So I put a link to the batch nested loop once, and it was the second part of one. Here is the other one. So those are examples coming from real cases. Users who wanted to optimize and get their queries scalable. And yeah, that's typically the case where we don't need, if the execution plan is scalable and in a few milliseconds, you don't need to do something physically except having the right indexes.
Okay, exactly. Okay. So thanks, Frank, for being a wonderful co-host for the Yuga by DB Open Hours in this season. Because as we said in the beginning, we are taking a Christmas break. So our next Community Open Hours session will be in mid or early January. We are yet to decide with Frank. And special thanks and big kudos to all of you who keep joining us, especially to Ash1 and to Pete, to our frequent attendees at these live streams. And thanks also to all of you who are watching us on demand. So keep coding, keep building, and enjoy the coming winter holidays.
Yeah, and see you next year.
See you. Bye-bye now.
Bye.